Okay, so in part two of the Mycielski construction, we're going to be beginning the process of coloring the new graph, which was two components, and we finally connected it to one component. So it's one new graph with 2n plus 1 vertices, and this is an increase from just the original graph having n vertices. Again, the goal is to show that if we color this new graph, we will have to have t plus 1 colors. The chromatic number will increase to t plus 1 instead of just remaining as t. So to do this, we're going to start something new, or we're going to actually use some aspects of this original piece from the first video. So what we're going to do is we're going to delete these, not because they're not existing, but rather that we cover this earlier, and I'm going to use the added space to do the coloring. The Mycielski construction is not complicated, it's just very cumbersome when actually performing. So what we wanted to show more in depth was why the chromatic number actually has to increase to t plus 1. So what we're going to do is we're going to say that there are multiple points called x. So each one of these, when we're working with it in like a computer program, when you're actually going through the process of employing an algorithm to perform the Mycielski construction, or really just to recalculate the chromatic number, at each current vertex being assigned or being worked with, they label it x. So x could change to be this vertex, or this vertex, or this vertex. It really doesn't matter. So it's just an assignment, a current assignment to specify which vertex is being worked with at one time. But what we're going to do is we're going to assign colors. And so what we're going to say is that all these points listed here in G are not adjacent, which means that they can have the same coloring. And we're going to color them alpha. So this is going to have alpha, this is going to have the color alpha, etc., etc. And so by coloring all of these alpha, what we see is this is the first step of the coloring process. What we're going to do now is we're going to go back up here. We're going to look at what x naught is. So x naught is this additional vertex. This is how we get the vertex size to increase to 2n plus 1. And what we're going to do is we're going to label it alpha, which we've already done. But if x naught is alpha, because x naught is adjacent to every single vertex in the independent set y, that means that the mates y sub x, all of the mates of the vertices in the original graph G, cannot be alpha. So what we're going to say is that y, the independent set y, is not going to be, or rather, alpha will not be an element of the independent set y. And this is pretty important because, again, this distinguishes the adjacency that we have here. And let's see, we get not an element in the independent set y. So now that we have this, if it isn't alpha, it has to be anything else other than alpha, and the range of colorings from 1 to t. And so we're just going to assign a different value, and so Dr. Trotter in lecture 9 assigns it as beta, so we'll do the same. And it really doesn't matter. We could assign it 4, 5, 18, z. It really doesn't matter. As long as it's a different color than alpha, and that specifies the non-adjacency with x naught. So we're going to label this beta. So now all these have a color of beta, and it's okay for all the vertices in the independent set y to have the same coloring because, well, they're all independent. So there are no edges connecting any two vertices in the independent set y. But now if we remember that all of these vertices in the independent set y are mates of the vertices in the original graph G, that means that it is okay for this current value of x in the original graph G to have the same color as that in the independent set y. So what we're going to do is we're going to, and it's not a first fit algorithm, but you can think of it like that. What we're going to do is we're going to essentially cancel out this color. We're going to now have the color beta. And so what we can do, and I can just cross out it with 2 segments. But the point is that that's not going to be a color anymore. Beta will be the new color of the vertex X in the original graph G. Keep in mind that now we're working in this big graph. This is a huge graph, and if we go back, see if I can actually, well, if we were to go back in time, we'd be able to see that we already had this construction connecting the mates y sub x to the original vertices in the original graph G X. So now that the vertices in G have the same color assignment as the vertices in the independent set Y, which is okay because they are non-adjacent, therefore they can have the same color, we look at the neighborhood of X. And so if we look at the neighborhood of X, they can't have the same color. It cannot be beta. It would have to be some alpha. But more than that, we look at alpha itself, or we look at these vertices themselves. It's okay for them to have the same colors because they're independent. And so because all these are independent, again, the points in the neighborhood. So what I would actually do is I'll redraw the neighborhood of X. So if this is the neighborhood of X right here, all the points that are within the set that is defined as the neighborhood of X will all be adjacent to X and therefore will not have a coloring of beta, but rather have some color alpha. And so I'll just move one of these over because we're not talking about at this point. So they'll have some color alpha. And remember, each of these points in the neighborhood of X was connected to one of the points in the independent set Y. It was connected to a mate. And I like to use this new terminology that we created. My partner and I, we call this the intermediate vertex. It really is an intermediate vertex because it's essentially establishing not adjacency between any vertex in independent set Y and the current vertex in the original graph GX. So if we were to connect all of these here, and this is very basically the same process that we had in the first video. If we do this again, we see, okay, this has to be alpha, this has to be alpha, this has to have a color of alpha, and this vertex in the neighborhood of X has to have a color alpha. And so if we look at our original count, originally we had a vertex count of, originally we had a chromatic number of T, but now we have a chromatic number of T plus 1. And you're probably wondering, where is this additional color coming from? Where is this plus 1 coming from? Well, think about it. Beforehand, we just had all alphas. But if we do our color assignment, if we're recoloring our whole new graph, we have to keep in mind that each of these vertices in the independent set Y has the same connection or same establishment that I'm showing here. Every single one of these vertices has that. And so if we reassign the color of X, the current vertex being analyzed in the original graph G with beta, and if we look at X naught, which has to have, or we're saying that it has an assignment of alpha, really we're really starting with X naught, the additional vertex, starting with a coloring assignment of alpha. We then know, okay, all the vertices in the independent set Y cannot have a coloring of alpha, which means that all of the vertices in G labeled X, the ones that we're looking at that are all independent, can have a labeling alpha, but we're going to recolor it because we have a new graph, beta, which means all these intermediate vertices, which is what my partner and I call them, intermediate vertices, which really are just the set of vertices that are in the neighborhood of X, must have a coloring of alpha. And because they have a coloring alpha, the chromatic number now becomes T plus 1. So I will write that the chromatic number, which is chi of G, now becomes T plus 1. And this is really due to the reassignment of colors using beta instead of alpha. So this is really important to keep in mind because this is how we arrived at this conclusion that the chromatic number would increase to T plus 1. So if we look again, so now we've arrived at this conclusion, if we look again, the goal of the Mycielski construction really is an explanation by contradiction, but that's not known or really inherently picked up at first. What we first want to do is we want to really prove that, hey, you can have a chromatic number of T with the new graph in total. But by actually performing the construction itself, we realize we contradict this, and we realize that we have to have T plus 1 colors. And so beta was not an element of the possible colors. We have to have this new beta, this new color, in addition to the existing range of colors T, which a number of colors T, we have to have a new color. So that's why we have this T plus 1. And so the reason why we really wanted to showcase the Mycielski construction, which is because it has so many relationships to the shift graphs, or the notion of shift graphs, where when we connect two vertices, or at least we call them vertices at first, when we connect them, that connection, that curved edge, if you will, no longer is a curved edge, but rather a vertice. And so we can actually confirm that we can color these with alphas, and we can see that if they're adjacent, they must have the different colors. We can see that in shift graphs by using the conclusion of the Mycielski construction.